Good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our lectures in thermodynamics. Today I want to look at steady-state conduction in composite walls. So when you're talking of composite means that has several components. Composite comes from the word components. So when you're talking of these composite walls, it means there are several walls. Let's take about three walls. And of course, I should say, in terms of in our earlier lectures, that all these are perpendicular to some axis. Let's call it x-axis. So let's call the first wall 1, 2, the other one 3, the other one 4. Now, these walls are made of different materials, but we are assuming, for simplicity, that all these materials, while they're different, the materials are isotropic. In other words, their properties are uniform. In other words, the surfaces, the temperature profile in that particular material is constant throughout, and so forth. And heat will be transferred, the rate of heat transfer in all directions, that material will be constant. So as far as the materials are concerned, we're assuming the materials are each isotropic, but they're different materials. Now, if you look at the interfaces, we have interface 1 and 4. You have the wall 1 and 4. This you can call them the outer walls. And wall 2 and 3, you can call them the interface walls. And you're making one key assumption that there is no resistance across the interfaces, So if you go back to the Fourier law, which we had seen in our earlier lectures, which says that the rate of heat transferred is proportional surface area of activity in terms of that heat transfer, the change in the difference in temperature, and the displacement. So that we have already talked about. That's the rate of heat, or what you call heat flux density, rate of heat transfer. That is temperature difference. That's displacement. A is area of activity, surface area. K is a coefficient involved in relation to the thermal transfer. So you can call it thermal transfer coefficient. Now, if we apply the Fourier law, to this particular system, then we'll see that, let's take care of the A, because we're assuming they have the same surface area, so let's just have Q, uppercase Q. This Q is equals to Q over A, that is equals to minus K12 into T2 minus T1 into T2 minus T1 over X12 in terms of the displacements. That must be equal to minus K23 into T3 minus T2 X23. That must be equal to minus K34 into T4 minus T3 over X34. So if we separate these equations individually, then we come up with a number of equations. So if we separate the equations, so I'm separating the equations. Always don't forget, we are dealing with a composite wall where we of different materials, and we have those interfaces which we have called 1, 2, 3, and 4. 1 and 4 are outside, 2 and 3 are involved in interface with the other walls. Now, so if we split these equations, then we are going to see that Q is equals to minus K1 to T2 minus T1 over X1 to Q. Again here will be equal to minus K to 3 into T3 minus T2 X to 3, and Q is equals to minus K 3, 4 into T4 minus T3 over X 3, 4. T, remember, temperature, X is displacement. And so we can further rearrange this expression. We can further rearrange this expression to simplify our lives. Further rearrangement. We can take care of these particular quantities here. We can take care of these particular quantities here. So we have, so that we can have Q. So we have Q. Let's take care of the negative sign by multiplying then this particular bracket, so that becomes T1 minus T2, that becomes T2 minus T3, that becomes T3 minus T4. So we have X12 over K12. If you take the K12, the coefficient there, and that displacement to the other side, to the right hand side, so we are left with T1 minus T2, and then we have Q X23 over K23 is equals to T2 minus T3, and Q into X34 over T over K34 being equal to T3 minus T4. That's a simple rearrangement. We have just taken that coefficient on the left hand side together with that displacement there. So basically this is straightforward. We have that rate heat transfer. That is just the thermal coefficient. We have the temperature. We have those black lines there. It is basically our displacement. So if we add these equations, if we add them and factorize, then we'll have Q into X12 over K12 plus X23 over K23 plus X34 over K34 will be equal to T1 minus T2. So we are done with that one. Then we add this one plus T2 minus T3. We're done with that one. Then plus T3 minus T4. We're done with that one. And so we see that some of those temperatures cancel out, like that cancels out, so that we have T1 minus T4. Important to note that we are now only having the temperatures of the outer walls, the temperatures of the outer walls, not the interfaced wall. But maybe if we had assumed there's resistance at the interfaces, then we would have the expressions for those walls, all the interfaces, including of the outer walls. But we have assumed, no resistance at the interfaces. So, working with that, so let's call this bulky quantity here, we can think of it as U. So Q then, Q into U will be equal to T1 minus T4. Or, on simplification, take U on that side, you have Q is equals to 1 over U into T1 minus T4. U here, this U here is the overall heat transfer coefficient for this steady state conduction in the composite wall. So U is the overall heat transfer coefficient. We can simplify that U. We can make that U simple by realizing that if you look at U, we have x12 k over k12. That's the length and the coefficients. x23, k23, x34, k34. We look at that and we see that the second term is not 1, that term is not 1. So we can actually express U. We can express this U in terms of summation. We can express that U, the sum of x, I, j, where I is equals to 1 to n, and where j commences from 2 to n. And so we can have that as our U. We can have that as our U, therefore Q. And express Q as T1 minus T4 over the summation equal 1. This starts from 2 x I j. So that's a very important expression for us. Remember, that's the overall transfer coefficient. We have left our k over k, kij over kij also. So this is a very important quantity. That's the overall transfer coefficient across that composite wall. Simple. We have made several assumptions. One, we are assuming that the walls are isotropic. In other words, they have the material properties of that particular system is uniform. So, and it's also isothermal. That material, we are not saying for the different walls, that's for each wall. And then the rate of heat transfer is uniform throughout that particular material. And we're assuming there's no resistance at the interfaces. So if you go back to our lectures where we looked at steady-state conduction, then you're going to see that there's significant differences. So let's stop at this particular point. We are continuing with our lectures.